Welcome back, my geometry students. Today we're going to start Chapter 6. Chapter 6 is all about quadrilaterals, four-sided figures. So if you look on the board up here, I have a family tree of quadrilaterals up here. And at the very top here is just then your basic quadrilateral. Nothing special about it. It just has four sides on it. So no matching sides, no necessarily matching angles either. So that's just your basic quadrilateral. Right below it here, you can see then is a subdivision of the quadrilaterals. On this quadrilateral though, you'll notice that the opposite sides run parallel with each other. And that's how it gets its name, of course. You probably already know that this is called a parallelogram. But what makes it a parallelogram again is that both pairs of opposite sides are parallel. Okay, our next shape here, which again is another subdivision yet of the parallelograms. So all of these classify as both a parallelogram and a quadrilateral. But on this shape, what makes it unique, you may have noticed, is that it has all four right angles. And again, the name for this shape comes from the fact that it has all four right angles. That's called a rectangle. Which, if you look at the name itself, if you never thought about it, literally means right angles, rectangle, right angles. Okay, this shape over here is a subdivision also of parallelograms, but is not considered a rectangle. It does not have right angles. It is a type of parallelogram. Its opposite sides are parallel, just like on a rectangle would be, and just a normal parallelogram. But this one, what makes it special is that all four of the sides are equal. So a parallelogram with all four equal sides is then referred to as a rhombus. You may have heard that term used before as well in your math classes. Somebody once in my previous math classes even said a rhombus looks like an abused square, like it's been shoved over. So it's kind of a square at a slant, you might say. Speaking of which, the square is our last of this branch heading down here of the family tree. And it qualifies as a rectangle, a rhombus. It's also a parallelogram and a quadrilateral. It's all of these. You might say it's the ultimate quadrilateral. So it has all four matching sides, just like the rhombus. It has all four right angles, just like the rectangle. And you know it as a square. Now there's a couple of other shapes that are quadrilaterals that we'll take a look at in this chapter as well. One of them is not in this branch of the family tree. Instead, it's off to the side over here. It's kind of like you might say the black sheep of the quadrilateral family. And it looks like this. Again, this is a shape that I bet many of you are already familiar with. Like the parallelogram, it has some parallel sides. This top and bottom on this one are parallel. The other two sides are not parallel though. So sometimes I jokingly say it's like your little brother or little sister that's always a step behind in the process of life. You know, you might have learned how to ride a bike and then went on to learn how to drive. And then your little sister or little brother is following behind in your footsteps. So they're a step behind. They're then learning to ride a bike as well. Eventually they'll learn to drive as well. So instead of having two sets of parallel sides like a parallelogram, its little half brother or little half sister is this trapezoid. It only has one pair of parallel sides, so it's only accomplished half of what the parallelogram has, you might say. But anyways, again, that's called a trapezoid. If you're wondering why it gets the weird name trapezoid, it turns out if you Google this, trapezoid is meant to mean a little table in Greek, I believe. So that's why they give that the name trapezoid. And one other shape that we will look at in quadrilaterals, again, is another offshoot over here, kind of another black sheep of the quadrilateral family. And it looks like this. And you might have guessed it. It is called what you think it's called. That is called a kite. And in a kite, what it has to be true then is that these two sides have to be congruent. Those two sides have to be congruent. So instead of having like opposite sides match on a kite, it's consecutive sides, 2 in a row, that are side by side like that. That's what makes that a kite. So in this chapter, we'll be studying all of these shapes in this family tree. Today is the focus on this first section of chapter 6 is going to be on parallelograms. Okay, so that's what I want to do now. So I'm going to go ahead and flip this over. And if you want to follow along with me in your textbook on section 1 of chapter 6, there are some postulates and theorems about parallelograms. Before I jump into those, let me start though with a formal definition. Let's start first of all with just a formal definition of what a quadrilateral was. Okay, a quadrilateral is simply a 4-sided polygon. We've talked about before what a polygon is. So in order to be a quadrilateral, it has to simply be a polygon that only has 4 sides. Then today, like I said, we're going to focus now on the parallelogram. So let's give you a definition of that as well. Parallelogram is going to be a quadrilateral, but it's a quadrilateral in which the opposite sides are, both pairs of opposite sides are parallel. So it's a quadrilateral with both pairs of opposite sides being parallel. Thus the name parallelogram. Okay, both pairs of opposite sides must be parallel. All right, so then that gets us into some of our theorems for this section. And all our theorems in this section then are going to be specifically about parallelograms. The first one on your list of postulates and theorems that you have there should be Theorem 6.1. Now, Theorem 6.1 is often confused for the definition of a parallelogram, but it's not. It's not the definition. In this theorem, Theorem 6.1, it simply states that in a parallelogram, if it starts off with if a figure is a parallelogram, then its opposite sides are not only parallel, but its opposite sides are congruent. Again, that's not the definition. It's its own theorem, that the opposite sides of a parallelogram will be congruent. Many of you probably already knew that or suspected that based on past problems you've done in your math classes. Okay, but that's Theorem 6.1. Theorem 6.2 again says something else that's true about parallelograms. So let me draw a little parallelogram here. And it's kind of like Theorem 6.1, only instead of opposite sides being congruent, it mentions in Theorem 6.2 that the opposite angles, so that angle and its opposite angle clear over here, and then these two angles that are opposite of each other are going to be congruent. Your gut instincts can kind of help on this. Both of those appear to be acute. Both of these appear to be obtuse. So, let your gut instincts guide you a little bit there. But this theorem then specifically states those opposite angles are congruent. Okay, there's a couple of more theorems here about parallelograms that are true. There's a theorem 6.3 that states that in a parallelogram, the consecutive angles, not opposite, but consecutive angles. So let's start by discussing what consecutive angles are here. But consecutive angles would be like 1 and 2 in this picture here of this parallelogram. Not opposite of each other. They're called consecutive because as you go around the figure, those two are two in a row, you might say, almost like they're neighbors or something. But those two consecutive angles, as we mentioned earlier back here on this problem, one appears obtuse, one appears acute. So they're not congruent. Instead, turns out that they will add up to 180 degrees. The reason this is true goes back to chapter 3. Remember back in chapter 3 we talked about parallel lines and when they're cut by a transversal. So if I were to ignore, for example, this side right here of the parallelogram, there's my two parallel lines. They're cut by a transversal. Those are a pair then of same side interior angles. And in chapter 3, remember we learned if the lines are parallel, that the same side interior angles are going to be supplementary or add up to 180. So, by the way, that means that there's all kinds of pairs of consecutive angles in this picture, because in a parallelogram, remember, both pairs of opposite sides are parallel. So 1, 2, 3, 4, let's number all of those angles. And now we could go on to say not only 1 and 2 add up to 180, but any pair of consecutive angles, 2 in a row. Like 2 and 3. 3 and 4. And finally 4 and 1. Okay, so any pair of consecutive angles like that are going to add up to 180. They're going to be supplementary. Equals 180. All right, so that gets us up to our last theorem. There's 6.1, 6.2, and 6.3. I'm going to squeeze our last one down here in this corner, and that would be theorem 6.4. And in this theorem, you might have figured out some of these ideas already about parallelograms, but this one might be a new one for you. In a parallelogram, so let me draw my parallelogram here. If you draw the diagonals of the parallelogram, so going from opposite vertex to opposite vertex, one vertex to its opposite vertex here. So if you draw those diagonals in, it turns out, according to theorem 6.4, that these diagonals will cut each other in half. Or remember, our term for that is to bisect each other. So this part will equal that part of that same diagonal. And this part will equal that part of that same diagonal. So the diagonals will bisect each other. All right, so those are the theorems that are in this section. Now I want to go ahead and just try some problems now. Okay, so let me clear my board here, and we can start trying some of those. All right. Let's start out with a problem that looks like this. And in this picture, as you could probably suspect, since this section's all about parallelograms, this is going to be a parallelogram. They would state that in the instructions. And they might mention that, for example, this angle here is 55 degrees. And, and really here, let me do this. Because there is a symbol a lot of times for a parallelogram. It's just a little miniature, just a little miniature parallelogram. So if I were to call this MATH, math, then we could call it parallelogram math. So in parallelogram math, we're going to find some missing measurements here. We're going to call this X, Y, Z, and W out here. So we're going to find all these missing angles. All right, now, let's say that I wanted to find, well, angle W first. The reason I'm going to choose angle W first here is because I notice in a parallelogram, again, the opposite sides are parallel, so these are running parallel. This is a transversal, and then that means this 55 and this W have a certain relationship, again, going back to chapter 3. Remember in chapter 3, again, we talked about parallel lines and when they're cut by a transversal. And if you look, 55 and the W are going to match each other. They're going to be the same because they're a pair of corresponding angles. You know, if I were to extend each of these out, you know, extend that, extend this, you know, extend this out a little bit, maybe then you can see it a little better. This angle you can see is the upper right, so that's why they have corresponding locations, and that means this angle here then has to be a matching 55, because in chapter 3 we learned that corresponding angles are going to be congruent. Okay, well, now let's say I wanted to find X up here. Okay, these two angles in a parallelogram are two in a row, or what we call, again, consecutive angles. And we just had a theorem 6.3, that said that those two consecutive angles are going to add up to 180. So off to the side here, we could just do some math, take 55 away from 180, and that's going to leave us with 125. So this angle X then has to be 125 degrees. By the same reasoning, this 55 and Z here, again, have to add up to 180. So you can do the same math. This would also be then a matching 125. And you could have found that in other ways as well. You got linear pairs, 55 plus 125 would add up to 180. Or you could even use that theorem 6.2 that we just covered today, saying the opposite angles of the parallelogram should match, should be the same. So 125, 125. Speaking of which, that last one there, opposite angles should be the same. This 55 means then that this up here, its opposite angle, has to match 55. So there's how you would find all those angles in that parallelogram given just one angle. And we were just given that one angle, 55 there. Based on that, we know consecutive angles add up to 180. Opposite angles should equal each other. You know, that's pretty much what you need to know about angles on a parallelogram. All right, now besides then an angle problem, we could give you a problem like this instead. Where maybe, for example, I'll tell you this length along here is 20. And by the way, we'll call this W, X, Y, Z. So in this parallelogram, W, X, Y, Z, like up here, I had you find W, X, Y, and Z. Well, down here, we're going to do that again, but I'm going to letter these a little different. We're going to find A, B, C, and D. All right, so let's say we've got some diagonals in this picture as well. Here's going to be A. It's going to be that part of the diagonal. This part of the diagonal, by the way, is 15. Let's see. This angle down here is 31 degrees. The angle right beside it here is 18 degrees. Oh, by the way, that's not 20. I'm sorry. That's supposed to be 2 times C. And down here, this side is 22. So there's A. B in this picture is going to be represented by an angle. B is going to be the angle ZWX. ZWX. So that's that entire angle there. So A is that, B is that angle, C is there. D that we're going to find is going to be another angle as well. D is going to be the angle WXY. WXY, as you can see, if you follow the letters, is that entire angle there. Okay, so here we go. Let's start out by finding A. A is pretty easy. We know, according to Theorem 6.4, that these diagonals bisect each other. So they cut each other in half. That means this half matches this half, as well as that half matches that half. But more importantly here, now you can see A is 15. Okay, so there's the A. Let's go ahead and do C while we're at it as well. C, as you can see, is involved in this side length, WX up here, although it's 2 times C on the picture. Its opposite side down here, ZY, is 22. And again, according to one of our theorems today, in a parallelogram, the opposite sides are congruent. It's Theorem 6.1. So I know that this entire length matches that entire length. Now you got to do a little bit of algebra. You know, 2 C's equal 22. So we just have to divide by 2 and find that C is 11. So there's our C. All right, now the angle problems. Okay, it kind of goes back to what we just talked about up here. So if I wanted to find angle B, which was this entire angle I marked up here in this corner of the parallelogram, I'm going to have to base it on some other angles that we know in this picture. Okay, if you look, its opposite angle is down here at the bottom. So this entire angle right there is the opposite angle of that one. If I were to add 31 and 18, you're going to see I get 49 degrees. So there's my answer for the entire measurement of that angle. That entire angle is 49 degrees. Because we know in a parallelogram, the opposite angles are congruent. Okay, then the next angle, angle D that I wanted to find here, was this entire angle. Well, that entire angle has a relationship with this entire angle, just like up here. They're consecutive angles in a parallelogram, so again, they should add up to 180. So if I take 49 away from 180, I'm left with 131 degrees for this angle right here. That entire angle then right there is 131 degrees. You could even, on this problem, going back to, like, say, this 49 up here, you could even break down each of the individual angles here because, you know, I know the overall is 49, but in a parallelogram, okay, remember that opposite sides are parallel. So this is parallel with this. Okay, and you see how this diagonal forms a transversal crossing them. So you got kind of a Z shape. See that? Where you go there and then down to here. Okay, so this 31 degrees that's down here, a part of this Z shape here, would match this top angle up here. Because those are a pair of, if you remember from chapter 3, those are a pair of alternate interior angles. So if that's 31, this is 31. Again, they form that Z shape. And then you can do it again. This one's parallel to this one. There's another Z shape. If you look at it this way, it goes here, then there, then there. See the Z? So this 18 here is going to match this 18 here. So down here it was 1831. All we're doing really is kind of flip-flopping them, switching them, because the alternate interiors would be here and there. Okay, so you'll have some problems like that where they might ask you to find different side lengths or angles. So now you're familiar with some of that. Some other things I want to try here yet before I call it a day. Would be a problem where you're going to have to do maybe some explaining. It's not a proof, but they might say something like this. You know, if I were to give you that angle 1 is congruent to angle 3 in, here, let's make a picture over here too. We're going to have like a parallelogram shape here, A, B, C, D. We're going to draw one diagonal here. There's 1, 2, 3, and 4. So if you're given that 1 was congruent to 3, and if you're given that 2 is congruent to 4, they want you to determine if the quadrilateral is a parallelogram. So if ABCD is a parallelogram. Okay, well, if you remember correctly from earlier in our lesson, our definition of a parallelogram said that to be a parallelogram, it's got to have opposite sides that are parallel. And that's what we're going to do here on this problem, is show that. We're going to show that the opposite sides are, in fact, parallel. And it has to be both pairs of opposite sides that are parallel. Because if only one pair is parallel, then it could just be a trapezoid. So we need both pairs to be. So if you look at the first statement, we had that 1 was congruent to 3. Okay, if you look at your picture here, again going back to chapter 3, you might notice those are a pair of alternate interior angles. And when those alternate interiors are congruent, making the Z shape again, see it? Where you go there, there, and there. See the Z shape? So if those are congruent, then that means these lines have to be parallel as well. So just based off of this alone, off of the fact that 1 was congruent to 3, we now know that this side DA and this side BC, or CB, those two sides then have to be parallel. So DA is parallel to CB because the alternate interior angles are the same. That again goes back to chapter 3. Now that's only one pair of parallel sides. Again, to be a parallelogram we need 2. So if you look now at the other pair of angles they mentioned, 2 and 4, if those two match, 2 and 4, then again it makes another Z shape. You know, this time here, I'll put this one in a different color. If you follow it, it goes from here, along there, down to there. And again, see how the 2 and the 4 are right in the corners of the Z? Okay, so they're a pair of alternate interior angles that are congruent again. But this time, instead of DA and CB being parallel, this time it's AB and DC. Okay, it's the same reasoning because of alternate interior angles are congruent, but it's a different pair of angles, of course. This time it's this pair of angles is the reason for that one, whereas the first one was that pair. Okay, so that's a way you can show that something is a parallelogram, is by simply showing the opposite sides to be parallel, using the definition of a parallelogram. All right, now let's say we had a similar type of problem, only this time, instead of it, just giving you some angles that were congruent like we did there, let's do a problem where I give you coordinates on an XY coordinate plane. And again, we're going to try to determine if the figure is or is not a parallelogram. Okay, so let's say that, let's say we got something like this where you got a point here at the coordinates 1, 1. Maybe another point along here at 6, 4. Another one out here, up here at 8, 9. And finally, one along here at 3, 6. Okay, we'll call this R, S, T, V. And if I connect those, you'll see they make a quadrilateral, but our job here is going to be to determine if this quadrilateral RSTV is a parallelogram. Okay, on a problem like this, I would expect you to show a little bit of work. Okay, don't just give it a guess and say, yes, it looks like one, or no, it doesn't. Okay, instead, we're going to determine this and have proof positive as to whether we know it's a parallelogram. Now, some of you might be looking at this and going, well, hey, let's just check the opposite sides and see if they're congruent, if they have the same length, using the distance formula. Okay, you're ahead of us. Okay, that would be a later section that we're going to do in this chapter. Okay, but in the meantime, there is another way to determine if this is a parallelogram in our first section here, and that's simply to use the definition. By definition, again, we need to show the opposite sides are parallel, and there is a way to show that. We can show in a XY coordinate plane if these lines are parallel by checking their slopes. So that's what we're going to do on all these problems. We're going to find their slopes. So we're going to find the slope of ST, for example, up here at the top. And of course, if it's going to be parallel to the opposite side RV down here, then these two should end up with the same slope. Okay, so we're hoping that these are going to come out the same here. Same with SR and its opposite side over here, TV. Those two, again, if they're going to stay parallel, have to have the same slope. Okay, and if you remember right, you find slope by subtracting your Y values on top, X values on bottom. So here we go. For S, we're going to start with the Y values, 6, and then here's T, has a Y value of 9. Okay, so 6 minus 9 on top, and on bottom for the X values, I'm going to put 3 minus 8. You're welcome to subtract those in the opposite order, just be consistent. Remember when doing slope, you just have to be consistent in your pattern. So I'm just going left to right, left to right. Now in my case, that's going to result in some negatives here. 6 minus 9 is -3. 3 minus 8 is -5. But remember, a negative divided by a negative is then a positive. So this is positive 3/5. Okay, let's go ahead and do RV and see if we get the same. So down here, your y value is a 1. We're going to subtract it from the other y value over here, 4. And on bottom, do the x values, 1 minus 6. Well, 1 minus 4 is -3. 1 minus 6 is -5. Just like above, you'll notice we get the same answer, positive 3/5. Because a negative divided by a negative is a positive. All right, so we got a match there. So far, so good. Now let's check these other two. Remember, you have to check all 4 because if only one pair matches, that only verifies so far that this would be a trapezoid, having one pair of parallel sides. Okay, but down here, for SR, again, we're going to subtract the y values on top. So 6 minus 1. X values on bottom, 3 minus 1. Well, 6 minus 1 is 5. 3 minus 1 is 2. So this time, this has a slope of positive 5/2. And then let's check TV. Hopefully we get the same thing, and if that's the case, then it will be a parallelogram by definition of a parallelogram. All right, so TV, y values are 9 and 4, so I'm going to subtract those on top. 8 minus 6 on bottom for the x values. 9 minus 4 is 5. 8 minus 6 is 2. Dun, dun, dun. It's a match. So you can see then that we have verified that this is in fact a parallelogram by the definition of parallelogram. Okay, so if any of those opposite sides are a mismatch, then of course the answer would be no, that it would not be a parallelogram. And those of you that were wanting to do distance of the opposite sides, don't worry, we'll get to that in our next, I believe it's our next section in fact. Okay, but for right now, I'd like you to try it with slopes, just to become familiar with that too. All right, so before I call this lesson a day, let's try a few algebra problems yet too. Okay, so like for example, let's say that we have a parallelogram here that we're going to call ABCD. And for our first one here, if this is a parallelogram, and if they told you that this top side up here is 5x minus 3, and this side down here is 2x plus 9, then I'm willing to bet that you can help me find on this one side AB. Okay, well, in a parallelogram, not only are the opposite sides parallel, but remember, according to theorem 6.1, those opposite sides are also congruent. So I would set those equal to each other. I'd say 5x minus 3 equals 2x plus 9, and I would solve for x. Okay, simple algebra here. You got a Sheriff Bandit situation, so I would get rid of the weaker one. Now you got 3x minus 3 equals 9, add 3. And divide by this 3 to finally get the x by itself. X would be 4. Okay, I'm almost done. Don't forget on this one, they did want you to find AB. So don't forget to plug that x back into here. So if we plug a 4 in for AB, 5 times 4 is 20, minus 3 is 17. So there's our final answer for AB. we'd say AB is 17. X was 4, but AB is 17. Okay, now, besides involving sides, you could have an algebra problem that may involve angles. So let's modify this a little bit. There's our parallelogram again, ABCD. But this time, let's say that angle A right here is 2x minus 10. And angle D is the other angle they give us, is 3x. And in the end, let's say that they want us to find angle C. All right, now with angles, of course, you got to be careful here. It depends on what angle relationship you have. Do you have opposite angles, or do you have consecutive angles, 2 in a row? In this case, I hope you see, these are not opposite angles. These are consecutive angles, 2 in a row. And we learned in Theorem 6.3 that those consecutive angles will add up to 180. So that's what we're going to do for our equation as well. We're going to say that the 2x minus 10, when added to this other angle 3x, has to equal 180. Had they been opposite angles, then of course we would have set them equal to each other. Okay, but in this case, since they're consecutive angles, they should add up to 180. All right, so in this scenario, we got a sheriff-deputy situation. Those are on the same side already, so go ahead and have them combine or join forces. Bring down the minus 10 and the equals 180. Now at this point, you're just trying to get the x by itself, so let's add 10 to both sides. That gets this one up to 190. And to get rid of the 5, we divide by 5. So in this example, x equals 38. Again, we're not done. Okay, in the end, they told us they wanted us to find angle C. Angle C is this angle right there. Not even one of the two involved in the problem. However, you get to now use the idea that opposite angles are congruent. So angle C is essentially the same as this opposite angle up here that was 2x minus 10. So we could just plug into that. We could just plug our 38 into that. So 2 times 38 would give you, let's see, 72. Minus 10 is 62 degrees. So there's our answer for this problem. Okay? So if the problem is an algebra problem involving angles, if it's opposite angles, they match. If it's consecutive angles, they'll add up to 180. All right, that should be enough instruction for you to be able to do the problems for your homework on this section, which is pages 295 and 296, problems 17 through 32. If you have any questions or need any extra help, please contact me. You can text me through Remind or send me emails, and I will get back to you. And I'm hoping soon to establish some office hours as well on Zoom, the app Zoom.